it really takes time because we need specific algorithms to calculate for this kind of ordinary system. So this we're going to focus on the logistic maps. Well, I proposed a robust Signum-Based chaotic maps. Okay, actually, you could see that this one is the well-known chaotic maps, well-known cubic map. The cubic map means xn to the power of 3. So the nonlinear is like this, of xn power of 3. And there are some variants, okay? This one I propose to use the hyperbolic tangent, beta xn. So we change the nonlinearity in this shape, but it still gives very chaotic features as well. But particular, in these papers, we present an alternative of the nonlinear terms, x to the power 3, or the hyperbolic tangent by using the hard-switching Signum function. This is the Signum function. I think everybody knows that the Signum function gives the value of -1 when it's lower than 0. If it's greater than 0, it's going to be 1. We use the hard switching Signum function. Let's see the result. This paper further generalized to Signum-based chaotic maps, okay? This is the equation that I proposed to you. It includes one linear terms and the Signum terms. This is non-linear terms. And for the Jacobian analysis, this one is in order to make sure that your system is not stable. If it's stable, it won't give you the chaotic signal, right? So we need it not to be stable. So the Jacobian analysis, this is the typical way. If the Jacobian is greater than 1, that means the system is unstable. And it is preferable in this case. And the equilibrium, for case 1, we get 3 equilibrium points. And case 2, we get 3 equilibrium points. You could notice one thing. The sign of each term gives different characteristics of the systems. Let's have a look here. I say my system is robust. Why? You can see from the bifurcation here. The bifurcation, there's no kind of, the thick area is really thick. There's no separations, okay? So this is robust chaos. We can use any value from like 1.4 to 2 like this, okay? Even the value change is still be chaos for the two cases. You could see that this one is the Lyapunov exponent. When it's greater than 0, the Lyapunov system is the parameter that indicates whether the system is stable or not. If it's not stable, it becomes positive. You could see that from this region, from 1 to 2, the value of Lyapunov exponent is greater than 0. This one as well. The two systems give the same characteristic of bifurcation and the Lyapunov exponents. But for the Cockburn plot, as I mentioned before, there are 2 or 3 fixed points. This one chose for the first system, the Cockburn plot is like this, but for the system number 2, the Cockburn plot is like this. This one is the 2 fixed points. And when you consider in the iterations from current stage and the next stage, it's going to go outwards from the fixed point. So each particular system has particular pattern of the Cockburn plots. And finally, you could see that this is the output signal in time domains for the two systems. They are randoms. Here, we use a very simple technique to get the random bits. We just stage coding using a very simple programs like this. And then we put the input by the post-processing system here, the chip register, in order to synchronize the clock. And for the test condition, of course, there might be a question, are you sure that your system is random, the output is random or not? Of course, we test by NIST, the National Institute of Standards and Technology of the United States. They provide a statistical tests in order to evaluate the randomness of binary sequences. So I generated about 1 million bits and put into these programs. There are 15 test methods and the p-values, okay? A p-value greater than a typical confidence level of 0.01, that the sequence is considered to be random with a confidence level of 99. You could see that for the 15 tests, we passed all